All right, so this is a continuation from yesterday's 5.1 notes. So by this point, we should all know that the electrons are on the outside of an atomic nuclei. So we have the nucleus in the middle, and the electrons float around the outside. Okay, that's a very important concept for this to make sense. So electrons are arranged in an atom so that the energy of the atom is low. This is so that atoms can maintain stability. If their energy is high, they're unstable. I was really going to go for more of a dramatic flow there, Zoe, but you really took the wind out of those sails. So the lowest energy state of an atom is called the ground state. If an atom is in its ground state, it is doing nothing. It's a lump on a log. If energy is added to the atom, that energy is absorbed by the electrons. And then the electron moves to a higher energy level. So a way to show this in a picture would be to have your nucleus, and you have your electron right here, and we're going to zap it with some energy. Thank you for the sound effects. And now this electron is going to scoot its way up to a higher energy level. Does that make sense? Energy levels are quantized. That means that atoms cannot absorb a random quantity of energy. Rather, it can only absorb quantities equal to the difference between the two energy levels. So it has to be a fixed quantity, and only the right amount of energy will cause an electron to go from the ground state up to an excited state. That leads us to the next vocab word. An excited state is when an atom's potential energy is higher than that of the ground state. So right here, this is the excited state of that electron. When an electron returns back to the ground state, energy will be emitted. So this electron will only stay in an excited state as long as there is a supply of energy to keep it there. Once that energy is gone, this electron will go back to its ground state. Electrons prefer to be in their ground state. It's a lot of work to get excited and be up in that higher level. The emission spectrum then is a pattern of lines formed when the light emitted from an atom passes through a prism to separate into the different frequencies of light it contains. Long story short, when an electron goes to an excited state and then falls back down and it releases that energy gets released in the form of light or some other wavelength along that emission spectrum. So if we look here at argon, the atoms in this particular example of argon are excited, and so the electrons are moving from that ground state and falling back down almost simultaneously. It's a constant up, down, up, down, up, down. And as they're falling, the frequency with which they are falling produces this purplish, pinkish color light. Helium will produce a much more light pink, so to speak. Neon gives us that orangish yellow glow. Krypton is white, and xenon is more bluish white. These emission spectrum of elements helps scientists identify the element. So helium, its emission spectrum will always produce this color. Neon will always produce the reds and the orange. Hydrogens is a red emission spectrum as well. So what this looks like is we have a gas tube that contains whatever element you're trying to figure out its emission spectrum. You send that light through a prism, and that light hits a black screen, and you will see all of the possibilities of the light produced for that particular element. Does that make sense? So each element you can do this for, and each element's emission spectrum, which is this, will look different. And so if you have an unknown element, you can perform this experiment and see what emission spectrum you get and compare it to a known element's emission spectrum. Does that make sense? Kind of like a little bit of detective work. So the Bohr model of the atom. So last we were with Rutherford's model of the atom, and that one was really all about the nucleus. But the Bohr model of the atom is really about the electrons now. Sometimes this is referred to as the planetary model. His model states that the electrons surround the nucleus and move in paths, and we call those paths orbits. The ground state is when the electron is in the orbit closest to the nucleus. As you move away from the nucleus, the electron enters higher energy states. So the bigger the atom, if an atom is supposed to have more electrons, the electrons have to move into these outer energy levels. The electron is not allowed to occupy the space in between the orbitals. So here's your nucleus. This would be an orbit. Here would be a second one. And the electron cannot be located in between. That's not possible because the energy is quantized to either be this amount or this amount, nothing in between. When an atom absorbs quanta of energy, the electron moves from the ground state to the excited state, like we've talked about. We refer to the ground state as n equals 1, and an excited state could be n equals 2, 3, 4, just depending on where the original which orbit the electron was originally located. And I think we said in the previous slide or two ago, the energy gained equals the difference in the energy between the two energy levels. And here we have a diagram that shows this, so that the energy from the first electron will be up here, and the difference will be the energy that's emitted. Okay, so here's your n equals 1 energy level. It's the closest one to the nucleus. N equals 2. If we needed more to supply homes, so to speak, to other electrons, it would be n equals 3. The highest it will ever be is n equals 7. Emission spectra are not equally spaced. This is explained by the Bohr model. If we assume that energies of various electron orbits are not equally spaced. So that is to say, going from n equals 1 to n equals 2 is not necessarily the same distance as it is from 2 to 3. Does that kind of make sense? So the closer your orbits are, the closer your emission spectra will show up. Does that kind of make sense? Do not assume that each orbit is the same distance from the previous one as the previous one was. Lots of previous's in that sentence. This is an example here of possible transitions for a hydrogen atom. Here, it can go from n equals 1 to n equals 2, n equals 1 up to n equals 3. And notice how each of these distances gets farther and farther from that ground state. So when they fall, they're going to fall and produce a different line in this emission spectrum. And every time an electron gets excited, which orbit it ends up on will be dependent on how much energy it absorbs. So if it only absorbs a little bit of energy, it's only going to be enough energy to get it to the n equals 2 level. If it absorbs twice as much energy, it's going to go twice as far, up into the n equals 3. Does that make sense? So if we absorb 3 quanta of energy, we'd end up in the n equals 4. So the Bohr model is great. It's getting closer and closer to the actual setup of an atom, but there are some downfalls. The first one is it only works if there's 1 electron. So that means it only works for hydrogen. And it couldn't predict the spectral lines if there was more than 1 electron involved.